Mesomeric effect, which is also known as resonance effect, is electron redistribution. Electron redistribution that occurs in an unsaturated, especially conjugated system. Please, that's conjugated system. I'm going to be explaining this one after the other. Electron redistribution that occurs in an unsaturated, especially conjugated system. Now, once I say unsaturated, you should know that unsaturated system is basically compounds that contain a double bond and also what? A triple bond. So not just all unsaturated system will undergo mesomeric effect, but the ones that are what? Conjugated. So now, first thing first, let's look at example of let's look at the example of a conjugated system. Let's look at example of a conjugated system. Now, this basically is going to help us to know that anytime you see this type of system, you should basically know that, oh, this mesomeric effect can occur here. So the first one is when you have two double bonds being separated by a single bond. This is a conjugated system. This is the first type of a conjugated system. The second type of a conjugated system is when you have a double bond being separated from a carbon that bears a negative charge. This is another unsaturated system, a conjugated system. The third one is, okay, let's call this guy, it must not necessarily be an atom, a carbon. Let's call this guy X, where X can be carbon, it can be oxygen, it can be anything. It must not be a carbon. So basically, anytime you see a single bond, a double bond being separated from an atom that has a negative charge, that's a conjugated system. A double bond separated from an atom that has a positive charge, that's also a conjugated system. Now, the fourth guy is when you have a double bond being separated from an atom that has a lone pair. That is a lone pair. Then anytime you have a compound that has double bond, single bond, an atom that is separated from each other by a lone pair. So we have four basic type of conjugated system. The first type is this, the most common, where you have a compound where two double bonds are separated from each other by just a single bond. A case where a double bond is separated from an atom with a negative charge. The third one, a double bond is separated from an atom with a what? A positive charge. And this guy, a double bond is separated from an atom with a what? A lone pair. So that's basically what we refer to as conjugated system. So anytime they ask you the effect that takes place in a conjugated system is mesomeric effect. Right? So take note of this system. Anytime you come across it in exams, on your textbook, know that they are conjugated system. So we said this is electron redistribution that occurs in an unsaturated system. Unsaturated simply means once you have a double bond or a triple bond. Please note that I can also, anywhere I have a double bond, I can also have a what? It's still the same thing. So not tomorrow if you see a triple bond and a double bond, you say it's not conjugated. It's still conjugated, right? So if you replace anywhere you have a double bond, that place can be a triple bond, right? So that is that. So let's look at features. Okay, fine. Features of mesomeric effect. Features of mesomeric effect. Number one, it involves the localization of electron. It involves the localization of electrons. Number two, it involves the complete transfer of pi electrons. All right, so let's proceed. Let's look at types of mesomeric effects. Remember we have types of inductive effects, We have the minus I, and we have the plus I. So we also have same thing for um, mesomeric. Types of mesomeric effects. Types of mesomeric effects. We have the first one, negative mesomeric effect. Now remember, I told us earlier that mesomeric effect is also known as resonance effect. So this guy, the negative can be called minus R or minus M. Take note of that. Then we have the second guy, positive plus R or plus M. So once again, this is very similar to that of inductive effect. So minus I basically refers to the electron withdrawing nature of atoms or group of atoms via polarization. While this guy refers to electron withdrawing nature of atoms or group of atoms via what? The localization I told us earlier. Let's look at the first one. Negative mesomeric effects. Please put down. Please put down. Negative mesomeric effects refers to electron withdrawing nature of atom or group of atoms via delocalization. Via delocalization. Via delocalization. Now you need to understand something, that anytime you attach any substituent that exhibits minus M in a compound, like basically attaching it to a carbon, what actually happens is that it pulls out electron from the compound, himself becomes negative, that's rich in electron, but the compound in which is withdrawn electron from becomes positive, decreases in what? Electron. So this minus M will always decrease the electron density of a compound. Because if you're pulling out electron from somewhere, you're decreasing the electron density in that compound, right? So examples of such substituents, so that you take note of them. NO2, this is nitro. We have CO, which is carbonyl. We have CN, which is nitrile. We have this. Now, these are all substituents that anytime they are being attached to a carbon, they exhibit minus N. But let me explain something so that you know the difference between minus I and minus N. Did you notice that nitro was also written in inductive effect, right? Some of these substituents exhibit minus I and also exhibit what? Minus M. Now, I have this. Now, this nitro is attached to a carbon that has a single bond. So this is going to exhibit positive inductive effects because sigma bond, right? But this guy is attached to a carbon that has a what? A double bond, right? So this is going to exhibit what? Mesomeric effect. And for this guy to actually further prove that this guy will exhibit mesomeric effect, the system that is present here must be a conjugated system. Must be a what? And I gave us 4 types of conjugated system, right? Now this NO, if you split this NO, this is a structure of this NO. NO2 is this. Remember I said Anytime you have two double bonds being separated from each other by a single bond, that's conjugated system, right? The first double bond, the second double bond, they are separated from each other by just a what? Or a double bond, a positive charge, and a what? A single bond. So this compound has a what? A conjugated what? System. This guy, you're even going further. Anytime you see any of this attached to a carbon that has a double bond, right? Automatically they will be withdrawing electron via delocalization. Via what? Take note of that. I'm going to show us that shortly. So take note, once any of this attaches to a carbon that has a double bond or a triple bond, mesomeric effect automatically. But if they attach to a carbon that has a single bond, what are we going to be experiencing? Inductive, right? All right, so let's look at the next guy. Positive. Positive mesomeric effect. Please put down. This refers to electron releasing nature or donating nature of atoms or group of atoms via delocalization. Via delocalization. Refers to electron releasing or donating nature of an atom via delocalization. Full stop. Now, this simply means example of such substituents. Let me give us example. O minus, OH, SH, anytime you have an atom a substituent that has oxygen on it, or sulfur or nitrogen, most likely is going to exhibit plus N. We don't really have to stress yourself, just look at this. Anytime you have this attaching to a carbon atom that has a double bond, now listen, you need to really understand how this guy works. If I attach this guy to any carbon that has a double bond, minus M automatically is going to take place. You attach this to a carbon that has a what? A double bond, plus M. However, if I attach this guy to a carbon that has just a single bond, I'm not going to experience minus M. I'm going to experience what? Minus I. Take note of that. So what you're attaching this substituent to matters a lot. So in exams, they might give you a compound like this. They might give you something like this and say which type of effect is, let's say, which type of effects can be seen here? Mesomeric or inductive? Why? Because there is a what? Conjugated system first. What is a conjugated system? Two double bonds separated by what? Once there is a conjugated system, there will be a mesomeric effect, right? Now, mesomeric effect is of two types, positive and what? Which type of mesomeric effect is seen here? It's not positive, it's negative. Now, look up. Which substituents? We have two double bonds, right? In that compound. Between the two double bonds, one of them will act as a substituent and the other one will act as a compound. Remember, the substituent is seen as what is causing the mesomeric effect, right? As I was explaining that if you take any of this and attach to a carbon that has a double bond. So now look up. This CO is this guy. Forget about this carbon that is added here. This CO is attached to this carbon that has a what? A double bond. So basically, this guy is going to be what? Minus M. Because CO as a substituent is minus what? M. Are you getting that? So you need to understand this. Imagine you also have something like this. Let's say I come here, I'll say CH2, CH. Which type of effect do we have here? First thing first, before you actually explain that, mesomeric effect, there must be a conjugated system, right? Is there a conjugated system here? No, right? There is. Now, this Cn is always written as this, right? Cn is always written as this, right? So there is a triple bond, which I can also call it double bond in this case. A conjugated system, this is a double bond or a triple bond separated from another guy by what? A single bond. So this is a conjugated system, right? Now, which of these is inducing the mesomeric effect? Is it this guy or this guy? Cn, right? Now, Cn, is it negative or positive? So which type of mesomeric effect is exhibited here? Very simple. So that is how you answer your question. You look at the question now. Which type of substituent is present? You get your answer and you're gone and you're done. So this is the first, or this is the second way question can be asked. So what we want to do now is to write resonance structures. Slash writing. All right, so please listen up. Now, how do we illustrate? Illustration of mesomeric effect is actually in terms of writing resonance structure. Example, you see something like, give the resonance structure of, now, first thing first, once you are asked to give a mesomeric resonance structure, you should be able to tell that for anything to have resonance structure, it must exhibit mesomeric effect. And for anything to exhibit mesomeric effect, there must be a conjugated system. Now look at this. This is an atom with a negative charge, a single bond, and a what? A double bond. It has passed the first test. Now this is an atom with a lone pair, right? A single bond and what? A double bond. Now look at this. Based on the substituent, based on what I gave us earlier, whenever this O, was it under plus M or minus M? This OH, was it under plus or minus? Plus. Anytime any of those substituents given to you is attached to a carbon with a double bond, right? You know there is mesomeric effect. This guy is going to exhibit positive mesomeric. And in positive mesomeric effect, is it electron releasing or electron withdrawing? Releasing, right? So this is what is going to happen here. This O has electron that is ready to release into this compound or to donate into this. This O has a lone pair that is ready to be donated into this. So this is what is going to happen. This negative sign comes here to form a double bond here, right? If this guy should form a double bond here, this double bond has to leave because you cannot have a double bond plus another double bond. The carbon will have 5 bonds. So this becomes this. Once you break it, you place it on the next carbon immediately. This is minus. Drag this minus to form a bond because this minus means 2 electrons, right? If you put this thing down, that means there will be a bond between this oxygen and this carbon here. Form a double bond. Is it not so? Now, you break this guy because you cannot have a double bond and another double bond here. You're going to violate the carbon valency here. So this becomes, I'm not going to write a one-head arrow. I'm going to write what? Two-head arrow, resonance. This becomes, this singular action will now form a what? Now form what? A double bond, right? Now we have this. Initially, there was a double bond here. This is how it's supposed to be, right? But this carbon will now have 1, 2, 3, 4, 5 bonds, which is wrong. So this act of breaking this thing simply means you put this minus that was here now, you've taken it to this point now. The first resonance structure. Meaning that this and this are the same. That means I can take this thing back and take this one back. This, I'll use this guy to form another double bond at this point. Right? And then break this guy and put the minus here. I'll come here. Here. Just follow the procedures. This singular action simply means this. O. This guy forms a double bond here, right? This action now double bond. This double bond breaks and put a minus here. And then you still have a double bond here on this side. So we are going to continue again. This minus comes here, form another bond here. And this bond does what? Break. Once you break, you put it on the immediate next carbon. This becomes O. This, which is this one already. This one now will now form a new bond here. This guy forms what here, right? So this, the last step, because we want to come back to this. This guy will now come here. When you form a new bond here, this one now break. We now have O. Now, if you notice, the bond has rearranged. Initially, the double bond was here, here, and here, right? Now it's now here. That is why most time benzene used to have circle at the center, right? That circle is more than the. So now let's count. This and that one is the same thing. Almost is this the right? So take one out of this. So this is the resonance structure of this guy is 1, 2, 3, and what? 4. And what is this compound? What is this compound called? This compound is actually, if you add H here, this is going to be phenol. If you remove the H, this is going to be phenolate ion. So in case you're asked, how many resonance structure does phenolate ion has? Or give the resonance structures of phenolate ion. This is a typical example of phenolate ion. So this is what you're going to do. This, we're still going to do the same thing here. This is still the same thing like this. Having a lone pair and having a negative charge is the same thing, the same electron. So if I want to do this, I can decide to put my OH here and decide maybe this guy, instead of putting it here, I can just decide to put it by the side. If I want to get the resonance of this, it's very similar to this. Take this lone pair of electron. We have 2 electrons here, you know so. If you drag this in like this, it means that one will keep on being with the oxygen and one will come down to this, thereby forming a what? A double bond. The same thing happens. You break this guy, you have this, you come down to this. This is going to be OH. Just watch what is about to happen here now. This time around, this O is already having, remember, oxygen is using one bond to bond with this O, also. So one bond from the hydrogen, 2, 3, right? So you have to put what? A plus on the oxygen. There was no plus here because oxygen is holding 2 bonds. Oxygen is very stable with 2 bonds, also. But if oxygen should hold 3 bonds, you must put a what? A plus. In the case of this phenol, once you form this double bond, put a plus on the what? O. Right? So here, you have plus here. Plus. Once you bring down this electron here to form a double bond, you must move this guy. It's a must. Right? So when you break this singular arrow simply means you break this bond, take the electrons, place it on here. Say it's going to be minus. The double bond remained here, and we also have this. The next one, take this guy, pull it down just to this point to form a double bond. You have to break this guy. Put it here. This becomes this forms a double bond here. This breaks and we have a minus here. The double bond here still remain. Now, this comes here, form a double bond here. You cannot have a double bond with this other one. So you bring this guy up to this next carbon. Have this. So you put this here. What is this? This comes here, and this becomes minus here. Once again, put this guy here. I bring this guy back here. There is already plus here. So if you break this thing, you're bringing this minus, right? This minus will now neutralize this plus, and it becomes just neutral. So we now have H, O. So just look at this carefully. All right, so let's have this. Let's have aniline. Now this is this. This is called aniline. And if you look at those compounds I gave to us earlier, NH2 is actually plus M, like positive mesomeric effect. Now there is a lone pair on this nitrogen, which obviously will be delocalized into the ring. The same thing is going to first thing first, this lone pair, once it delocalizes, it forms a double bond here. We have this. We cannot have a double bond here with this double bond, so this guy has to go. It's 1 minute. So we have this, right? So this becomes, we form a double bond here. So we have H2 double bond. Once again, class, any compound that this guy, this first atom is not having minus, right? Once you form the double bond, if you must put plus, it's only when it's having minus that once you form a double bond, you're not going to put plus. This guy is not having minus. The previous compound OH was not having minus, right? All right, so here, so this guy, you move this guy to this point to form plus. Battery slow. So here, we form this a double bond. This becomes this. All right, so this singular movement puts a minus here. We have a double bond here. We have this. This will continue. This forms a bond here. This guy breaks and put the minus here. So we have double bond minus this. This come back here again. Have this. Now the double bond retains here. This minus now forms a new double bond here. And this double bond breaks and forms a minus here. Now this guy comes back here, forms a double bond, and this guy goes back, neutralizes this plus. So have this, have this. All right, so this becomes, so this guy has 4 resonance structure. 1, 2, 3, 4. So most times you may be asked, how many resonance structure does so compound has? It's not something you can just look at and tell the answer. You have to write it out first, like we just did here, and after which you tell the answer. Okay, application of mesomeric effects. Applications of mesomeric effects. Right, acidic strength comparison between alcohol, phenol, and carboxylic acid. And the second guy is basic strength of amine. Please look up. Now for the first one, I'm going to take the first one. So, and let's look at this. First, let's write out all their formulas. Alcohol is this. Let's use okay. Alcohol is this. Example of alcohol is CH3, CH2, OH. Now phenol is this benzene ring that has now this is phenol. Carboxylic acid is this. Now this is CH3, CH2C. Now look at this. Now these three guys basically can be considered as an acid, basically, because they all have the capacity. Alcohol, the first one is alcohol. The second guy is phenol. The second guy is carboxylic acid. Now, three of them can be considered as an acid because they all have the tendency to donate hydrogen. This, and this. But one thing you need to really understand is that what really makes, one of the properties that makes something to be acidic is not just the ability to release hydrogen. But after you must have released the hydrogen, how stable would you be? Right? Imagine you have 10,000 naira and you give out the 10,000 and you're broke. And somebody that has 20,000 and give out the 10,000. Which of those two guys will be more stable after giving out? 20, right? So basically, after these guys had given out the hydrogen, how would they now fare afterwards? If this guy should give out this becomes CH3, CH2 minus plus what? H plus. If phenol should give out, let me just remove this guy. If phenol should give out hydrogen, here becomes what? Minus plus H plus. If this guy should give out hydrogen, this becomes CH3, CH2C double bond O, O minus plus H. But listen, after this explanation, I'm going to give us the reasons. Because in the exam, they might ask you, why is phenol more acidic than alcohol? Right? They will not really ask you that of carboxylic acid because this guy is purely an acid. Right? Acid is always going to be stronger than something that acts as an acid. Carboxylic acid is an acid, no doubt. So the major comparison is always between alcohol and what? Phenol. Now, why is it that phenol is considered to be more acidic than alcohol? Both of them can act as an acid because they can donate hydrogen ion to give H plus, right? But after donating the hydrogen ion, how would they now fare? So after giving out the hydrogen, this is what we are going to have here, and this is what we're going to have here. If you noticed, this O minus, this charge will be delocalized. After giving out the hydrogen plus, the charge on the alcohol would be localized. Localized simply means, imagine putting 50 liters of water on your head for a very long time. Your neck is going to pain, is it not so? If you cannot, you're going to break the bucket, right? But imagine somebody that if you're putting 50 liters on your head, if you're tired, you pass it to another person. While the other person is holding it, you're stretching your neck. That's what we call delocalization. Like electron is moving from one place to the other. That makes it to be more stable. If something is localized, it makes it to be unstable. Because after a very long time, it will not be able to continue again. Right? So, if this guy should give out this hydrogen, the charge on this O will not be able to spread. Why? Because there is no conjugated system here. Electron can only distribute in a conjugated what? Is there a conjugated system here? So after this guy had given out the hydrogen, there will be no conjugated system left, right? So this guy will be very unstable. Will be very, very what? But look at this phenol. After giving out the hydrogen, there is a conjugated system here, so. So when this guy is tired holding this guy, it will pass it to this guy, so. The same stuff we did previous. This charge will go around. Before it will come back to this oxygen, right? This guy have regained strength to carry it on. You keep on passing, it can continue till next year. But this guy, the moment he gives out this hydrogen, the charge is localized. Class, once a resonance is possible in a compound, compounds that exhibit resonance are more stable than compounds that do not exhibit resonance. Right? Compound that exhibit resonance are what? More stable than that do not exhibit what? Another key point I would like us to take home is that the more resonance structure a compound has, the more stable that compound would be. If a compound has 5 resonance structure and another one has 2 resonance structure, which of them will be more stable? 5. So the reason why phenol is more acidic than alcohol, let me detect it so that we'll just have a straight key point without lots of words. Please put down. Phenols are more acidic than alcohols because the anion of the phenol will be resonance stabilized. Phenol are more stable than alcohol, are more acidic than alcohols because the anion of phenol will be resonance stabilized via delocalization. Because the anion of phenol will be resonance stabilized via delocalization. So somebody asks you, why is it that phenol is more acidic than alcohol? Because of resonance stabilization. Phenol can exhibit resonance stabilization after giving out hydrogen, but alcohol cannot or will not be able to exhibit resonance stabilization. And I just explained now. The anion of this phenol is this. This guy has a conjugated system. So because of the conjugated system, this charge will be delocalized. It will be redistributed around this stuff, whereas this guy cannot be distributed. Right? So that is it.